So this isn't about nuclear reactions. So the nucleus contains protons and neutrons. In this case, two protons, making it helium. And those protons are pushing each other apart. But there's something called the strong force that holds the nucleus together, and all particles in the nucleus are exhibiting this strong force, and they create stable isotopes. So the stable isotopes are shown here in red, and in the center where there are lots of transition metals, there are multiple stable isotopes. And sometimes, occasionally, there's no stable isotope. And the thing we're going to pay attention to now is these unstable isotopes that undergo nuclear change. And so they have nuclear chemistry or nuclear changes. So we call that radioactivity when you feel the emission, when the emission of energy or energetic particles are released. We know that it's radioactive because it's emitting particles and changing. It's a nuclear reaction, so it's taking place in the nucleus, whereas chemical reactions take place as we change the bonds, rearrange the bonds between elements using electrons. So when radioactivity changes the nucleus, it may be unstable or it may be stable. After the change, it'll often emit a particle, and it always emits energy. There are three principal types of radioactive decay. They are listed here from highest to lowest. The terms alpha, beta, and gamma are Greek letters for A, B, and C. And the alpha particle is found first because it's a helium nucleus and it was pretty large. And so its interaction with film was apparent. The beta particle is an energetic electron and was discovered next. And finally, gamma rays were discovered along with X-rays. And so the discovery of them gave them the name A, B, and C. The gamma rays are the highest energy, and the alpha particle has the highest mass. Because the alpha particle has a high mass and a large nucleus, it has a hard time getting through something as simple as thick paper or plastic, because it interacts with the nuclei of the matter that it's traveling through, and that stops it from traveling further into or through the material. Whereas beta particles are very small, a small electron, and they travel easily through thin or very low density material, but get stopped in something that's more dense like wood or foil. And then finally, a ray of light, like gamma ray, is able to travel through non-dense material when it has such high energy, and is only stopped by concrete or lead. And lead is that when you get teeth x-rays, they put a lead vest on you to protect you because the x-rays won't get through lead. Now, radiation's all around us, and so while it can be damaging, you should recognize that it's present all the time. When you're out in the sun, you get cosmic rays. If you were in the Northeast, radon is being released from the ground all the time. It's being released from concrete around you. Safe medical procedures use it for tracing and identifying what's happening with medicine as it's going through. And in fact, if you eat a banana, you're getting a small amount of nuclear radioactive material in your potassium. Some terms you need to know are decay, emission, and capture. Decay and emission mean to make or produce a particle, and capture means to add. So here we have alpha. That fish is a Greek alpha sign, or Greek A. So alpha decay is where that alpha particle is produced, and that's a Greek B, beta particle. is where an energetic electron is produced. There's a gamma symbol. Neutron has the number on top is the mass number, so it's a mass of 1, and the bottom number is its atomic number of protons, so that's 0. And then a proton has a mass of 1 and has 1 proton. So these are all the symbols you need to know. An electron being captured is added before there's a change. And here's the neutron too. So here's some color-coded examples. Here at the top, we have an alpha particle, that's the helium nucleus, and it's on the product side, so we say alpha decay. The next one down, the slightly orange, is a beta particle, that's the energetic electron, and we say beta decay and beta emission. The term electron emission is often used, so you need to be aware that that might happen, and then there's a gamma, that's the same. When the particle, I'm on example number 4, is on the reactant side, then you say capture. So in the 5th example, we have an electron capture or beta capture. And down below, the blue neutron is on the capture side, so we'd say neutron capture. And then the green proton is on the decay or emission side, so we say proton emission or proton decay. We still have reactants and products, and I've been saying reactants and products. In a chemical reaction, the atoms, the type and number of atoms are conserved. So we have 1 calcium on both sides, we have 2 hydrogens on both sides, and 1 oxygen on both sides, but we've rearranged the bonding. For nuclear reactions, we rearrange where the neutrons and protons are, but the total mass or the mass numbers are the same on both sides, and the total mass, the total atomic number is the same on both sides. So the blue numbers add together. This is the equal sign, and the purple numbers add together, which are atomic numbers. Now we'll be switching it, we'll be adding that beta particle, which will have a negative charge or like an opposite proton. And so we say conservation of charge sometimes to represent what's happening with the charge and why that negative value comes up. And here we see that negative atomic number showing up down here. All right, so this one is showing some of the things we can do. One, you could name what this is. This is an alpha decay. There's the alpha particle, and it's on the product side. But moreover, we want to be able to figure out what this unknown isotope is. So we set up a simple algebra problem and solve it for both the top and the bottom. So then we get 230 and 89, and now the two sides are equal. We'll be using the symbol, the number 89, and we'll go to the periodic table, and from the periodic table, we'll find the symbol AC. And then the next one, we do the same thing. We make a simple equation on top for mass number. We make a simple equation for the atomic number, but this time the atomic number includes the -1. And then we use the 85 on the periodic table to find the AT or astatine. All right, so that's what we do. The nuclear reaction could get a little more complicated with more particles, but the process is the same and not too hard. And when we have a coefficient, here's a coefficient with the neutron, that coefficient shows up in two places: for the mass number it's used and for the atomic number it's used. And so we'll have to create equations with these coefficients too. This wasn't part of an online one, but you could certainly practice with each of these. There are no answers being shown, but we're going to talk about them. So then the very first one, what did we make? So that's a beta particle, and because it's on the opposite, on the product side, we say what type of reaction this is. It's a beta decay or beta emission. I'm going to skip down to the third one. This is an alpha particle, but now it's on the reactant side, so I could say alpha capture. Now I just said alpha capture, so you can have word equations too. So this number 3 is an alpha capture by bismuth 234. So bismuth 234 plus the alpha particle in number 3 is called alpha capture by bismuth 234. And we'll talk more about how to set these up in a couple more slides. So we had to learn what decay and capture were. We had to learn what alpha, beta, and gamma are. And we also need to know what fission and fusion are. Fission is where I separate a nucleus into 2 smaller nuclei. And so a memory device is fission and scissors. Not very good, but they both have ISS in them. A fission is where a nuclear reaction breaks it apart, and we use these in nuclear power plants. One of the reasons we have nuclear waste is when we take uranium and break it apart, we can end up with more unstable radioactive particles, and so then we have radioactive waste. The main reason we have radioactive waste is that nuclear power plants are only 95% efficient. Standard nuclear power plants are only 95% efficient, and so a lot of the material gets left behind. That would be like having a gigantic hole in your gas tank while you're driving down the road. Fusion is the other one, and my memory device is union. And so by putting particles together, we get a union of those particles. Fusion takes place in the sun when it joins hydrogens together to make helium. It then goes on to do more small molecule combinations, hydrogen and lithium, to make lithium, and carbons combine and oxygens combine. And then we call that the life cycle of the sun, or of the stars, which is an interesting topic. So we see fission as large masses breaking down into smaller masses, and we see fusion as some smaller masses being combined. The second example shows you how difficult it might be to see a fusion. But if we make larger nuclei, which we'll see with the mass numbers, then we did fusion. A typical multiple choice question is actually just which one is an alpha particle in number 1. So that's A, the helium nucleus, so you had to memorize those terms. Here we have an isotope symbol of 200 and Hg. So a lot of people pick 200, but it's actually 200 is total number of particles, so this represents the mass, all the protons and neutrons. And then Hg tells us the atomic number, which is 80 protons, so that's B. This has a beta and an alpha. Beta, alpha, which of these is correct? So the beta is not on the decay or emission side, only the alpha is on the emission side, so that's why it's D. And then if we combine the top, we get 210 on the reactant side. So 4 plus what equals 210, and we end up with 206. So now only B and C could be right. Repeat that process and do a small equation, and we end up with B. An energetic particle that can pass through one thin sheet of material but is stopped by a thicker piece, that's beta, the in-between one. Alpha would be stuck right away, and gamma would travel until it hits something super thick or super dense. Chemical reactions are different. Nuclear reactions, this is what we've been talking about. Changing the atom, creating new isotopes, emitting radiation, all those are aspects of a nuclear reaction. Only a chemical reaction shares and transfers electrons to make new bonds. This is kind of difficult. Remember, the 88 represents a proton and neutron combination, so this isotope, strontium-88, has 38 neutrons or 38 protons. And it turns out that the atomic number of strontium is 38, so it has 38 protons. And finally, the most energetic particle is gamma, but gamma is not listed, so the next one we know of is beta, and so we list beta. Protons are pretty energetic too, so maybe you chose B. And electron is not energetic electron, so beta is more energetic than a simple electron. Okay, so here's some review. So you should practice these, so please stop the video and determine the answer. We also want to know what the name of the reaction is. Okay, so we go through the simple math, and then using the atomic number, we have determined what they are. So 28 is nickel and 21 is scandium. And so this is just more practice. It wasn't supposed to be hard. The next thing you do is name the reaction. So to name the reaction, we just have to identify these particles. So what particle is that? Same thing here. And then we have two new particles at the bottom. So what's that? Beta, beta, that's a neutron, that's alpha. Okay, and then identify whether they're products or whether they're reactants. If they're products, like in 9, it's a decay or emission. If they're a reactant, they're a capture. So this neutron is captured and the alpha particle decays. And then this is the one where I said we're going to have a little bit more time to talk about it. So this is a word equation, and the most important thing to do is to write this out first. This is my beginning. So I will tell you an isotope, and I'll tell you two reactions. So this isotope gets written first, right? And the 82 came from the periodic table. And then which one of those is a reactant, a capture or a decay? So the capture is the reactant. So the neutron will be captured and the alpha will be decayed. Okay, then we just go through the same math we did before, and we find the mass number and the atomic number and use the atomic number for the symbol. If you're interested in more social concerns about nuclear reactions, Chernobyl happened many, many, many years ago, more than 20 years ago. And in fact, there's a forest fire now in Chernobyl, generating, lifting up some radioactivity from the forest floor, but not too much concern in the Ukraine. And then Fukushima is a recent disaster where a power generator that was well protected was swamped by an unusually large tsunami because that generator kicked out a lot of the safety measures, and one of the nuclear power plants collapsed. And now Japan will aim for having zero nuclear energy, and Germany has already said zero nuclear energy. And this is of concern because nuclear energy does not create carbon dioxide, which contributes to global climate change. And so what we'll need to do is think about that, which would happen in a typical class. And you can think more about that right here with the US. So thank you. I appreciate that you wanted to pay attention and look at what was happening. So thank you.